it's time to talk about classes of isomers. Isomers, according to the official definition, non-identical compounds having the same molecular formula. So there are two main classes of isomers, constitutional and stereo. Constitutional isomers, they would have a different name according to sort of routine IUPAC naming. That's a weird way to say that, I know, but something like 1,2-dimethylpentane, 1,2-dimethylcyclopentane versus 1,3-dimethylcyclopentane. Those have the same formula, C7H14. That's the exact example 2 videos ago. But they are definitely different compounds. Stereoisomers are also different compounds, but it's not always easy to tell that at first glance. Stereoisomers have the same connectivity, 1,2-dimethylcyclopentane and 1,2-dimethylcyclopentane, but they're actually different in three-dimensional space. So we talked about conformational isomers, even though we didn't exactly called them that previously. We're not actually going to talk about amine inversion at all, but we've talked about rotation. That was our Newmans and our chairs and stuff. When the chair flips from axial to equatorial, when a substituent on a chair flips from axial to equatorial, that's a conformational isomer. They're spatially arranged different, but you cannot separate the axial version from the equatorial version because it's a constant flipping back and forth. Okay. Configurational isomers are things that can be separated because they are two different molecules. There are two main classes under configurational. That's cis-trans, the stuff we've talked, some of the stuff we've already talked about, and isomers that have asymmetric carbons. Ooh, that's another video. Cis-trans isomers, alkenes can have cis-trans isomers, and cycloalkanes. Well, let's take a quick look at cycloalkanes, since that's just a refresher on things we've already discussed. So these are cycloalkanes that are considered cis-trans isomers. Why are they cis-trans isomers? They both have the same connectivity as far as what is attached to what, but spatially they have different arrangements. Bromine and methyl are pointed down in this one. Bromine and methyl are pointed opposite directions, one up, one down in this one. So if you consider the hydrogens as well, you could say both hydrogens pointed up, same side, cis. Hydrogen one up, one down, different sides, trans. These are cis-trans isomers, also known as geometric isomers, different arrangement in three-dimensional space. So cis-trans isomers have a thing called a stereocenter. What is a stereocenter? An atom upon which interchange of any two groups generates a stereoisomer. What? This carbon is a stereocenter because if you unplugged and swapped the H and the Br, you get a different compound that would turn this cis compound into trans. This carbon is also a stereocenter. Same reason, unplug the methyl and the hydrogen, plug them in the other direction, it's a different compound. Yep, here too. There are two stereocenters in these molecules. What's a stereocenter? An atom, upon which interchange of any two groups generates a stereoisomer. That's a word we will use somewhat frequently, but there's a lot of definitional terms within this unit. So start working on that one. Okay, the other option of cis-trans isomers is alkenes. Alkenes, what's the hybridization of an alkene carbon? This guy, sp2. sp2 carbons are trigonal planar. Trigonal what? Trigonal planar. Planar? That means that all of the carbons, all 6 carbons are in the same plane. Those yellow highlighted carbons are in the same plane. So this is a three-dimensional sort of picture of it. Those 2 dashed carbons going behind the plane, these 2 wedged carbons coming toward you, and there's this purple blob above and below. That's the pi bond. That's the electrons being shared across the middle to make a pi bond. Pi bonds cannot rotate. In order to turn something like this, which we would call cis, because the 2 similar groups are on the same side, 2 H's on the same side, point the same direction, in order to turn something like this cis into this trans, we would have to break the pi bond in the middle. It's being shared here, no more sharing, it's being shared again. We broke the pi bond. Rotation around a pi bond, not a thing, cannot happen. What does that matter? That allows us to talk about alkenes being cis or trans as well. So when you're looking at alkenes, two hydrogens or two similar groups on the same side, cis. Two similar groups on opposite sides, trans. There's another picture of the same molecules. But you're looking at these similar groups to designate it as cis or trans. And what we mean by on the same side, that means like these wedged hydrogens up here are on the same side. They're pointed the same general direction. Alkenes are only capable of having cis-trans if the stuff, the two things, if these two things are different, on both sides, actually, that's the only way you would ever consider having cis-trans isomers. It is very possible to not have cis-trans isomers in an alkene. So we can run through a little bit of naming of alkenes and isomers of alkenes. If you have very similar groups around your alkene, you can use the name cis-trans. But cis-trans is not good enough always because your groups are not always similar. So, you guessed it, IUPAC, the International Union of Pure and Applied Chemistry, came up with the EZ system of nomenclature. It's not difficult, it's EZ. So, EZ says if your two highest priority group, it's all about priorities, if your two highest priority groups are on the same side, we're going to call it Z. If they're on opposite sides, we're going to call it E. Okay. So he said IUPAC came up with the rules, but really the rules of naming E and Z is called using the Cahn-Ingold-Prelog system of priorities. Here's a quick recap of most of the Cahn-Ingold-Prelog rules. Atoms with higher atomic number get higher priority. That will decide a ton of the cases. These are actually written in order. That will decide a ton of the cases. If you have the same atom but a different mass number, like carbon 12 versus carbon 13, higher mass, higher priority. Students often get stuck on this rule and say, this branch has a higher mass, so it's a higher priority. This only plays a role in isotopes. Be careful. This is a very specific rule that really doesn't apply to many examples at all. If the atoms on the stereo center are the same, follow the path to the first point of difference. We'll see some examples. There's this weird double bond rule with Cahn-Ingold-Prelog that says, treat it like there are two of that things attached. We'll talk about that as we go along. Give me a second. Let's run through some simple examples first. So looking at these four alkenes, they are configurational, geometric, cis-trans isomers, whatever. If we name this top one, we would call it a butene. We would call it a 2-butene. Yes, I know we haven't named alkenes yet, but I think you can probably even dissect why the name of that thing is 2-butene. I trust you. This is also 2-butene. But these are absolutely different molecules because, remember, rotation cannot happen around a double bond. So we cannot convert one isomer to the other through rotation. So we have to name them differently because if we name them differently, it's acknowledging that they are different compounds. So I can consider my two hydrogens here and ask the question, are those hydrogens on the same side or are they on opposite sides? That would be, those two circled things would be considered the same side. It ain't that. So that would make us call this trans. These are on the same side. That would make us call this cis. Cis and trans applies to things that have similar groups. Halogen, 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 carbon. I don't know what to call a similar group on this bottom example. So what do I do? That's where the EZ system, comes in to assist. The EZ system says, look at the two groups connected to your alkene and assign priorities to them. So in this top example, I've got a carbon and a hydrogen. Hydrogen up here. My mouse is really not showing up today. Hydrogen up here, carbon down there. Comparing those two, the first rule says atoms with higher atomic number get higher priority. So that means carbon is higher priority. That leads to me saying this whole bottom branch is higher priority than hydrogen. Okay, consider the other side. Over here, I'm considering carbon versus hydrogen again. Who's a higher priority? Obviously, the higher atomic number. So that's this branch. So if I consider my two branches that have stars on them, those two starred branches are pointed opposite directions. So opposite directions means E. I could call this molecule E2-butene. Because our next example has the exact same things connected to it, I'm going to point out this guy as the high priority and that guy as the high priority without discussion much about it. But that would be those two high priority groups on Z, same side, so that's Z2-butene. So these top examples could be called cis or trans or E and Z. Either way. That's cis or trans is only allowable when your groups are similar, but down here, these groups are not so similar. So let's see priority-wise how we would name that one. If I compare chlorine to fluorine, that's comparing the two groups on this carbon, chlorine to fluorine, higher atomic number, higher priority, chlorine, higher atomic number. Bromine compared to carbon. I'm not comparing to CH3, I'm comparing atoms directly. So bromine compared to carbon, higher atomic number, higher priority, up here. Those two high priority asterisk groups are on Z, same side. So that's the Z isomer. We're not going to name the whole thing. Over here, hydrogen versus carbon. Here, hydrogen versus carbon. Carbon's a higher atomic number, higher priority. On the left-hand side of this molecule, carbon versus fluorine. Fluorine is higher atomic number, so fluorine gets higher priority. So I would also call this a Z isomer. This last example is sometimes confusing to students because if you tried to name this last one as a cis-trans isomer, you actually technically could name it a cis-trans isomer. If you're looking for similar groups, this CH3 and that CH3, I would not only call those similar groups, those are the same. So the yellow highlights make me call this thing trans. Sometimes students associate the term cis with Z and the term trans with E. That's not really the case. Trans and cis means similar groups. E and Z means priority stuff. We now interrupt your regularly scheduled programming to bring you a biological side note, aka why do you have to take organic if all you want to do is go to med school? Let's look at fatty acids. Fatty acids have a few different varieties. Fatty acids could be called saturated. That's what happens if they have no alkenes present. This top example is stearic acid. It's a saturated fatty acid. Fatty acids could be called unsaturated if they have at least one alkene in them. So this is oleic acid. There's the alkene. I can tell that's where the alkene is because that's where my kink happens. That's a cis alkene because, as it turns out, all naturally occurring fatty acids have cis double bonds. So here's oleic with one double bond. Here is linolenic with 2 double bonds. And here's linoleic with 1, 2, 3 double bonds. That makes this whole thing really curly. Is it good to be curly or not? Well, I'm willing to bet you've heard of fatty acids in the dietary and nutritional world, but you didn't really know much about them. That got real crowded, I apologize. Fatty acids, the end of a fatty acid chain, the tail end way down here, the end of a fatty acid chain is called the omega end. It looks like a little W, it's an omega. If you count backwards from the omega end, you find an alkene on carbon 3 of the omega end. Ooh, you ever heard of omega-3 fatty acids? Yeah, I bet so. Fish oil has a lot of omega-3s in them. If I keep counting backwards, I get to carbon 6. You ever heard of any omega-6 fatty acids? Yeah, maybe. This one is omega-9. Omega-3, 6, 9 is really what this fatty acid that I've drawn is. Those are usually marketed as good for your dietary needs. So some of the dietary fats are simply omega-3s, or simply omega-9s, or simply omega-6s. Some of them have multiple. What I've drawn here is a polyunsaturated fat. There are 3 alkenes in my fatty acid. Okay, how do fatty acids relate to fats? Fats are known as triglycerides. Oils are also known as triglycerides. So here's glycerol. It's got 3 alcohols on it. If I take some fatty acids, like those we just drew, those we just saw, and the one we drew, and I turn those alcohols and acids into an ester functional group, when all 3 of those alcohols become esters, that's called a triglyceride, a triacylglycerol. So this is a triglyceride, but that triglyceride might be considered a fat or it might be considered an oil, depending on the chains of your fatty acid that are connected. If those chains are all saturated, it's most likely going to be a solid at room temperature, and anything that's a solid at room temperature is a fat. Officially, coconut oil is a fat, even though we call it coconut oil. It's a solid at room temperature. Anything that has kinks in it is likely to be liquid at room temperature because those kinks disrupt the stacking. Figure coming in a second. Those kinks disrupt the stacking of the molecules, leading them to not have such strong intermolecular forces, leading to them being an oil, a liquid at room temperature, also known as an oil. So here's the stacking that I mentioned. These with saturated chains stack together well and tightly, leading to a long bit of intermolecular forces, a long area where dispersion forces can hold those things together. But when you have even one leg that has a kink on it, even one fatty acid that has a cis alkene in it, you get liquids at room temperature, most likely, because they're no longer packed into a good crystal structure. So fats versus oils, that's how it really works. It's all about alkenes and bonding.